grade 11s, welcome to this lesson on identities. Hooray! Yeah, we're so excited. Let's have a look at what we know so far. The quotient identity. The quotient identity is where we know that tan of an angle, let's say theta, that tan theta can be rewritten as sine theta divided by cos theta. Now, we have proven this identity in previous videos, so we're not going to run through that now, but this is an identity that we've used quite a bit already. Your square identity is that sine squared theta plus cos squared theta is equal to 1. And again, we've proven this previously, so we're not going to run through that now. But just to show you that your square identity can be written in 3 different ways. We can also say that sine squared theta is equal to 1 minus cos squared theta, and how cos squared theta is equal to 1 minus sine squared theta. So it's important that we remember that these two guys are an option of my square identity, because as we start simplifying expressions now, we're actually going to see how often those two different options pop up. Okay, so this is what we know so far. Let's get stuck into our first example. So grade 11s, for my worked examples, I've taken questions from exercise 4 in your textbook. Okay, so what we are doing here, if I actually just put down what our instruction is to simplify as far as possible. All right, and in order to do that, we're going to need to use these identities that we were talking about earlier, our square identity and our quotient identity. Okay, so example 1 is sine x divided by cos x times tan x. So first handy little trick from me is whenever you see a tan, you must switch it to sine over cos, right? Most times, especially if you see a sine or cos nearby. It's kind of then where the question is leading. So the numerator, sine x, I can't do much about that right now. So I'm just going to leave it as sine x. And then cos x, again, can't do anything about that. But I'm going to rewrite tan as sine x over cos x. Now, this cos x that's next door to tan, I can write it as cos x over 1, just so you can see then how the cross cancelling is going to happen. So now I can see, well, those can cancel each other out. They're just the same. And I'm left with sine x over sine x. Those two terms also cancel each other out. So hey ho presto, check it out. Your answer just simplifies to 1. Isn't that awesome? All right, so here's the second expression that we need to simplify. Tan squared x times 1 minus sine squared x. Okay, so there's actually 2 things happening here. I can rewrite tan squared as sine squared x divided by cos squared x, right? Remember, that's our our quotient identity. And 1 minus sine squared, think back. Let's go back. Right, back to your square identity. We're going to use this. Right, it's these ideas here that are now happening. So if we have a look, 1 minus sine squared x is the same as cos squared x. And now you should be able to see what we can do. We can now cross cancel the 2 cos squared x's. So your final answer, we can just say, is sine squared x. Super chilled. So similar thing happening here in question 3, right? We've got the 1 minus cos squared, and we know that 1 minus cos squared can be written as sine squared from our square identity. So in the numerator, I'm going to change it to sine squared, and we're just dividing by sine of x. So this is the same as saying simplify x squared over x, right? Your answer would just be x. So the same thing happens here. The sine x cancels out with one of the 2 sine x's at the top. So your final answer would just be sine x for question 3. Right, now with this one, so something very important, grade 11s, you are often going to look to factorize in these questions. Okay, it's very often where factorizing happens. So for this one, we can see that 8 is common to both terms. So I'm going to take out 8 as a common factor. I'm going to be left with sine squared theta plus cos squared theta. Now you should be able to recognize what this is, right? This is your square identity. And we know that sine squared theta plus cos squared theta just becomes 1. So our answer for number 4 is just 8. It's easy, right? So easy. Alright, so number 5, it looks like there's a lot going on. But let's just approach this piece by piece. So the 1 I'm just going to leave as 1 for now. Then I see tan x, so I'll make my quotient identity sin x over cos x, right, multiplied by cos x times sin x. Here's our sin x right at the end. So now what we can see again is that there are terms which we can cross cancel. And if I now simplify this, it's going to be 1 minus sin x times sin x, which will become 1 minus sine squared x. And there's your square identity again, grade 11s. And we can simplify 1 minus sine squared x to become cos squared x. Okay, so that looked a little bit hectic to start with, but actually it's pretty easy. So let's look at this last one where we're just trying to simplify the expression as far as possible. So I've got these two brackets. So I think what I'm going to do is I'm going to use FOIL, right? I'm going to expand my two binomials and let's see what we get. So we have 3 times 3 is 9. Well, we can actually kind of see how this is a difference of 2 squares. But anyway, okay, so we've got 9 plus 9 sine theta minus 9 sine theta minus 9 sine squared theta. All good. So what happens? These middle terms are going to fall away. We are left with, what are we left with? We're left with 9 minus 9 sine squared theta. So again, factorize. Common factor of 9. We're left with 1 minus sine squared theta. And you should see where this is going. That 1 minus sine squared theta just becomes cos squared theta. So your final answer would just be 9 cos squared theta. Okay, so that was all of exercise 4. Not too bad, hey? Nice and quick and easy. So all we've been doing here is simplifying expressions. The next part of the video is now going to focus on proving identities. Alright, grade 11, so we're going to start proving identities now, and we are not going to have an identity crisis. What we're going to do is, our goal is to show that the two sides are equal to the same expression. So I'm meaning the two sides from the equals to sign, right? So you're working on the left-hand side and on the right-hand side. Now, it's very important that you do not treat this like an equation. What you want to do is you just want to make the left-hand side look like the right-hand side. Simplify each expression on either side of the equals to sign and make them look the same. So you cannot, let's say, subtract from both sides or multiply onto both sides. You need to manipulate either side to make it look like the left-hand side or make it look like the right-hand side. So let me just show you what I mean by jumping into our first example. Alright, so here we go. Let's get stuck in. You'll notice that this really looks like an equation, right? There's an equals to sign, but it's not, grade 11s. What we're trying to do is we're trying to simplify each expression on either side. You want the left-hand side and the right-hand side to look the same. So don't subtract 2 sine theta from each side or do weird things like that. You are going to work on the left-hand side and you're going to work on the right-hand side. Treat them separately, and at the end, ask yourself, do my two sides look the same? So working on the left-hand side, so this is what I do. I literally say left-hand side is, all right, cos theta times my quotient identity. Tan is sine theta over cos theta plus sine theta. My right-hand side, well, the right-hand side is 2 sine theta. Now, I can't do anything with this, grade 11s. Like, this is an identity. Sine theta is an identity. I can't change anything here. So I'm going to leave the right-hand side. And I'm going to keep working on the left-hand side and hope that I can make the left-hand side look like the right-hand side. But I know that I can. We got this. So those cos thetas cancel out. And I'm left with sine theta plus sine theta, which is 2 sine theta. And look at what we've done. Oh my goodness, they are the same. So you know what? Therefore, the left-hand side is equal to the right-hand side. So you have proven what we've set out to do. Aren't you amazing? Let's have a look at example 2. Alrighty, let's check out example 2. So again, there's a lot going on the left-hand side. We've got 1 on the right-hand side. So in this example, we might need to manipulate both sides. Okay. So let's start off by working on the left-hand side. Let's see what it has in store for us. Okay, so sine x is just sine x times cos x. Okay, there I see tan. So we're going to rewrite that as sine x over cos x plus cos squared x. All right, so I know that cos squared x, we know that cos squared x is 1 minus sine squared x. So maybe we can make that adjustment now, but let's just see what happens if I keep going. So these cancel each other out. And also, grade 11s, this is the really nice thing about identities, is that there can be multiple ways of answering the same question. So now the left-hand side is sine squared x plus cos squared x. And I know that that is my square identity. That is 1. And if we remember, if we look back to what the right-hand side was, the right-hand side was 1. So hooray, we've proven that the left-hand side is equal to the right-hand side. Amazing. So what I was alluding to now was another way we could have done this. We could have still made the quotient identity here and done that simplifying, and then we would have had sine squared x plus, and cos squared x we know is 1 minus sine squared x, and then if we simplified that, sine squared x minus sine squared x, we would have just been left with 1. Okay, so this is just another option that you could have taken. You could have also made the right-hand side be sine squared x plus cos squared x. And at this stage, you've proven that the left-hand side equals the right-hand side. Okay, so grade 11's identities are really great because often there's more than one approach that we can take to answer the question. All you have to do is make sure that the left-hand side looks like the right-hand side, and then we are smiling. Let's have a look at our example 3. So I know now we're seeing fractions and we're going eq, but none of that. It's nice and easy. We're working on the left-hand side and we're looking at the right-hand side. And let's go. Simplifying the left-hand side. So sine squared alpha is the same as 1 minus cos squared alpha. So I'm going to rewrite the left-hand side as left-hand side equals 1 minus cos squared alpha divided by 1 minus cos alpha. If I look to the right-hand side, the right-hand side can't really become anything else, right? The right-hand side is 1 plus cos alpha. Again, you might be saying, but I see 1, and I know that 1 can be sine squared alpha plus cos squared alpha. But I don't always like to do too much manipulating to start with, because this right-hand side is looking quite simplified already. So I'm just going to leave it like this for now and see where I'm going over here. So I hope you realize that you mustn't just cancel things out now, right? It's 2 terms over 2 terms, so we can't do that. I need to factorize the numerator here. This is actually a difference of 2 squares, because 1 is a perfect square, And the square root of cos squared alpha would just be cos alpha. The same as how the square root of x squared would just be x, right? So that numerator, we factorize. Let's write that down. We're going to factorize. And the method of factorizing, it's a difference of two squares. So 1 plus cos alpha, 1 minus cos alpha, and we have that all over 1 minus cos alpha. So now I can just pop the denominator, those terms into a bracket, and say, amazing. Those things cancel, or those brackets are the same. They cancel each other out. So we just left with 1 plus cos alpha on the left-hand side. What is the right-hand side? 1 plus cos alpha. Amazing. So what have we done? We've done it again. We've therefore proven that the left-hand side is equal to the right-hand side. Awesome, hey? This stuff's pretty nice and straightforward. I hope you're enjoying it. Let's do one last example. All right, so I've saved the best for last because I know now you're going, oh my goodness, what is happening? But it's actually not as bad as it looks. So remember, what we want to do is we want to focus on the left-hand side and we want to compare it to the right-hand side. We want them to look the same. Now, I know that this looks a little bit intimidating. Let me rewrite that as something very familiar. If I, instead of writing sine squared theta plus 2 sine theta plus 1, imagine I said x squared plus 2x plus 1. Deal with that. You would say, this is a trinomial, Claire, and I'm going to factorize that trinomial to x plus 1, x plus 1. So I hope you realize that this is exactly the same. You're just factorizing in terms of sine, not in terms of x. So the way I factorize this very easy trinomial over here is exactly the same as the way I'm going to factorize this trinomial. If you want to use the variable x or another letter instead, then simply replace it with sine theta. That would be perfect. So working on the left-hand side, we now have in the numerator sine theta plus 1 times sine theta plus 1, right? That factorized trinomial. In the denominator, I have cos squared theta, which I'm going to rewrite as 1 minus sine squared theta. Okay, so left-hand side is looking pretty good. I factorized the numerator. And now I hope you realize that we're going to also factorize the denominator because the denominator is a difference of two squares. Cool. So I've got sine theta plus 1 times sine theta plus 1. And that is going to then be that difference of two squares. The factorized brackets will be 1 minus sine theta times 1 plus sine theta. Oh my goodness. Now look, we've got one term over one term. We can cancel out brackets, terms which look the same. So my left-hand side, when it's fully simplified, is sine theta plus 1 divided by 1 minus sine theta. What does my right-hand side look like, grade 11s? So my right-hand side is 1 plus sine theta. So sine theta plus 1 and 1 plus sine theta is exactly the same, right? Both those terms are positive, so the order doesn't matter. And the denominators are identical, so hooray! We've proven that the left-hand side is equal to the right-hand side. And we've also proven that you are amazing. Well done, everyone. I hope you enjoyed the video and that identities is not intimidating to you from this point on. It's actually quite straightforward and fun to do. Enjoy!